extracting gold from electronic waste, a step-by-step breakdown. The video presents a fascinating hands-on demonstration of recovering pure gold from electronic scrap, specifically gold-plated connector pins. This process, often called urban mining, transforms discarded electronics into valuable precious metal, while the narrator simplifies it as something anyone can do anywhere. It's a complex chemical procedure that requires a deep understanding of significant hazards. Let's walk through the narrated steps and expand on the science and critical safety realities behind them. 1. Preparation and initial dissolution. The process begins by weighing the electronic scrap gold-plated pins removed from old circuit boards or connectors. These pins are not solid gold. They are typically made of a base metal like brass, an alloy of copper and zinc with a thin layer of gold plating. The pins are placed in a container, covered with water, and then treated with nitric acid. This is the first critical chemical reaction. Nitric acid is a powerful oxidizing agent that aggressively attacks and dissolves most base metals. The copper, zinc, and other impurities enter into solution as metal nitrates. However, gold is a noble metal, meaning it is unreactive and does not dissolve in nitric acid alone. At this stage, the gold plating is physically freed from the underlying metal, breaking into tiny particles or flakes that settle as a sludge. The boiling observed is an exothermic reaction, indicating the vigorous dissolution of the base metals. 2. Filtration and washing. Once the reaction subsides, the mixture is diluted with water to help neutralize some of the acid's strength, and then carefully filtered through a fine cloth. This cloth acts as a sieve, capturing the solid particles of gold and any undissolved impurities, while allowing the toxic metal-laden nitric acid solution to pass through. The narrator emphasizes thorough washing to ensure no microscopic gold flakes are lost. This acidic wastewater, containing dissolved copper, nickel, and other metals, is a serious environmental pollutant if not handled properly. 3. Purification with hydrofluoric acid. A surprising and extremely dangerous step follows. The addition of hydrofluoric acid, HF, the narrator states it boosts the acid's power to remove remaining impurities like silica or glass fibers that might have come with the scrap. HF is notoriously hazardous. It causes severe, deep tissue burns that are often not immediately painful but can be fatal. Its use outside of a controlled laboratory with specialized equipment and training is exceptionally risky. After this treatment, the mixture is filtered and washed again, theoretically leaving behind a cleaner concentrate of gold particles. 4. The mercury amalgamation process. This is a pivotal and highly controversial stage. Mercury is introduced and stirred into the container. Mercury has a unique property. It forms an amalgam, a kind of alloy, with gold. The tiny, fine gold particles adhere to the liquid mercury, separating from the lighter dirt and debris. Baking soda is added to reduce surface tension and improve contact. Once amalgamated, the heavy mercury-gold mixture is collected and poured into a cloth. When the cloth is squeezed, the liquid mercury passes through its pores, leaving behind a semi-solid amalgam ball inside. This method, while historically used in gold mining, is now widely banned or strictly regulated due to the extreme toxicity of mercury. The vapors and skin exposure pose severe neurological and organ damage risks. 5. Separating gold from mercury and final refining. The amalgam ball still contains a significant amount of mercury. To retrieve the pure gold, the amalgam is treated again with nitric acid. This acid dissolves the remaining mercury, leaving behind the purified gold particles. Heating accelerates this process, turning the mixture white as murky compounds form before eventually being driven off as vapor and other major inhalation hazard. The now purified gold dust is washed repeatedly to remove all traces of acid. To transform this dust into a solid nugget, it is mixed with borax, referred to as swaga, which acts as a flux. The borax lowers the melting point of the gold, dissolves surface impurities, and protects it during melting. Finally, the gold is melted with a torch into a single, shiny bead or button, representing the recovered 24-karat gold from the original e-waste. Critical analysis and real-world context. While the video presents a seemingly straightforward path to profit, several crucial points must be emphasized. Severe health and environmental dangers. This procedure uses some of the most dangerous chemicals available: nitric acid, corrosive, toxic fumes, hydrofluoric acid, potentially lethal, and mercury, a persistent neurotoxin. Performing this without a fume hood, proper personal protective equipment, PPE, chemical training, and waste disposal systems is incredibly reckless. The completely legal claim is highly dubious for an individual doing this at home in countries like the US, UK, or Canada, which have strict regulations like EPA, OSHA, or REACH governing hazardous waste handling, air emissions, and chemical disposal. Economic realism. The claim of making $1,000 to $2,000 from scrap totally free. It ignores the initial cost of scrap, chemicals, specialized equipment like acid-resistant containers and filters, and crucially, the cost of safe waste disposal. The process shown also loses measurable amounts of gold at every stage in filter clause, in solutions, and trapped in mercury. Professional refineries used more efficient, closed-loop processes like aqua regia digestion or electrolysis to achieve near-total recovery. The bigger picture of e-waste recycling. Professional electronic waste recycling is a vital industry. It prevents toxic substances from landfills and recovers not just gold, but silver, palladium, copper, and rare earth elements. However, it is done in large scale, regulated facilities designed to protect workers and the environment. The informal or backyard recycling depicted often in developing countries is a major source of environmental contamination and severe health problems for communities. In conclusion, the video provides a visually compelling glimpse into the chemistry of gold recovery. It correctly demonstrates gold's resistance to nitric acid and its property to amalgamate with mercury. However, it dramatically understates the profound dangers and practical complexities involved. This process is far from a safe, legal, or profitable DIY project for most people. It serves better as a striking illustration of the hidden value within our discarded electronics and the sophisticated, hazardous processes required to extract it responsibly. The true gold in modern e-waste recycling lies in developing safer, more efficient, and environmentally sound technologies to manage the growing global tide of electronic scrap.